Basically, a few weeks ago, there were ideas tossed around for the next Sim Academy presentation, and the guy in charge basically said, we want to do a really simple presentation that doesn't cover any advanced topics, and for some reason, I suggested we do excessive pivot ratios, and someone said that'd actually be a good idea, so here we are. The purpose of this presentation is to discuss this fatal error message, user fatal message 9050, run terminated due to excessive pivot ratios. I only have 45 minutes, so although I'd like to cover, some people, when I asked what should I present in here, some people chimed in and said you should cover, linear algebra and matrices and things like that. Really, I figured that, for this, I should keep this as simple as possible, and that I should try to keep it as brief as possible, too, and just try to cover maybe, I'll take the Apple approach. I don't want to cover every possible cause of excessive pivot ratios. I only want to cover about 90% of them. Now, the other thing is that while I was preparing for this presentation, I actually started to write a long PowerPoint. It came out to be about 30 or 40 slides, and I basically scrapped it and said, really, what would really serve you guys better is if I basically took all that information and compiled it into a no more than 5-page long write-up. So basically, instead of using a PowerPoint to cover this with you guys, I basically tried to boil it down, condense it, and write it into a no more than 4-page write-up that I can email to you guys or you guys can download after this presentation. So then basically if somebody asks you about excessive pivot ratios, you might be able to just email them this write-up, and hopefully they can debug their model, or you can as well. So let's go ahead and do the actual presentation. So here I am, I got this fatal message, excessive pivot ratios, and the first question that people ask is, well, what do I do? Well, if you get this fatal error message, first thing I recommend is you look above the fatal error message, and you get this guy, this warning message, and it basically says, here are the excessive pivot ratios. The first question that a lot of customers ask is, what does this mean? Well, an excessive pivot ratio is Nastran's way of saying that, there's something wrong with your stiffness matrix. Your stiffness matrix is basically not solvable. The two most common reasons for why a stiffness matrix is not solvable is that the model is not constrained or that elements are not connected. And we're going to get to that. But basically, in that situation, what happens is that entries in your stiffness matrix are actually zero. But Nastran, being a numerical solver, doesn't actually get zero. It'll get something like, 0.0001 instead of 0. So what happens is that we actually calculate the ratio of that, and then we basically put this up on the screen. So, for instance, here, I've got some excessive pivot ratios. You'll notice, for instance, that some of the values are negative, some of the values are positive. Sometimes that can give you a hint as to what's wrong. The other thing is that, sometimes you can look at the degrees of freedom, and that can give you a hint as to what's wrong. So, basically, if you get this fatal error message, first thing I recommend you do is you take a look at this warning message and take a look at the nodes that are listed and the degrees of freedom that are listed. If you're using a GUI like Patran or SimExpert or HyperMesh or whatever, see if you can highlight this node for this error message. And that's what I'll do in a couple of examples that we'll see very soon. Look at the area around these nodes for the problem. And when I say look at the problems, well, we're going to cover that very soon. One thing to be careful about is that oftentimes the nodes that are listed in this fatal error message are not the exact problem node. For example, Nastran's just a computer program. So if you have the entire left half of your model unconstrained, it's going to show you the first couple nodes in the left half of the model, but it won't show you exactly where you need to do the constraint. So a lot of customers, when they see this fatal error message, they'll correctly deduce, oh, there's a problem with this node 387 or this node 11,077, and they'll look only at that node. Don't do that. If you get this error message, look at the area around this node and look for specific problems. Generally, it'll be a constraint or an element connection problem or a stiffness problem. I basically put a couple notes here on what you can do to interpret this. Like, for instance, you'll notice if you look at this warning message and you see a negative factor diagonal, most of the time when you see this, it means that somewhere around this node, you've got something unconstrained. The other hint about that is if you look at the degree of freedom. For instance, here, node 1198 has an excessive pivot ratio in T3. So that means that in order for you to have a problem in T3, it has to be a constraint basically it's got to be a constraint or something doesn't have stiffness in T3. Because translations, generally when you see translations listed here, the only way you can fix it is with a translation. Sometimes when you look on here, you'll see rotations. Rotations doesn't necessarily mean you need to constrain that rotation, because if you, for instance, constrain two nodes in T1, you could actually fix out the R2 direction. So when you see translations listed here, it means you should look at translations. But if you see rotations, it means you should still look at your translations as well, is what I'm trying to say. Another thing about this is, take a look at the types of elements that you've got here. So, for instance, I put a little note here. What if node 11077 belongs to a solid? Well, solid elements only have stiffness in the rotational directions. So that means that what's happening is that you've accidentally connected something else to node 11077. Because normally, if this node belongs to a solid and you see an R2, normally the rotations would have been constrained out by Nastran automatically. So you've got something else in the model. Either this is actually a free-floating node, or this is you've got a spring or a rod that you've accidentally connected to your solids, and that's what's causing this problem. So again, when you're looking at this, and I realize this is kind of advanced, but when you get this fatal error message, take a look at the warning message that's above here, and at the very least, this at least tells you what area might be the cause of the problem. And then, as you guys get better at diagnosing these fatal error messages, you might be able to deduce what's wrong just by looking at the degrees of freedom or the stiffness values themselves. Is it positive? Is it negative? Is it really large? Like these guys are pretty large. These guys at e to the 7, I put a little note here that by default, Nastran will automatically fatal you if you get an error message of e to the 7. So, for instance, you'll notice here, these are just slightly above e to the 7. You might be able to get away with just adjusting the tolerance in Nastran or using bailout. But I only recommend that when you have a model that can almost pass. And towards the end of the presentation, I'll try to cover bailout and max ratio with you guys for a little bit too. So let's go ahead and cover some specifics. So I basically said that if you get this excessive pivot ratio problem, you should bring up this node and look at the area around this node for certain problems. Well, what do I mean by certain problems? Cause number one for excessive pivot ratios is bad constraints. Let's bring up a model that I know has bad constraints. So let's see. Here's a model with some bad constraints. This model, just to give you guys an idea, it's a plate with a hole in it, and for the loads, I'm going to just basically put this guy in tension. There we go. So basically, it's kind of hard to see, but you see this 100 here? Maybe if I zoom in, it'll be a little easier to see. This 100, basically I'm putting 100 psi on this edge. I'm putting 100 psi on this edge, and it's basically yanking this plate in tension. For the constraints, I've decided to basically try to keep this as simply, simply support this guy. So I've got a constraint here in the one direction and 5 and 6 to basically allow this guy to shrink due to Poisson's effect. And I've got another constraint here in 2, 4, 6. Again, I want to allow this. I want to basically allow this guy to stretch since this is a load in tension. This is a two-dimensional problem, So basically my entire model exists in the XY plane, and I only have loads in the XY plane. So if I go ahead and run this, basically what's going to happen is that I'm going to find that this model failed, and a couple of you guys might already notice that the reason this is going to fail is that I don't have any constraints in Z. So let me get this job running. So that's what I'm trying to say here. You need to constrain your model at least in all three translations. Even if you don't have a load in one of the directions, all three translations need to be constrained. So a lot of times when you're looking at constraints in the model, don't think about the load. Look only at the model and make sure there's a constraint in X, a constraint in Y, and a constraint in Z. And then after that, you need to look at the rigid body rotations. Remember that you don't necessarily need to constrain the rotational directions. For instance, if you have two nodes constrained in the X direction, that can couple out a possible rotation in Y and Z. Also, a lot of customers just assume that if you have nodes constrained in 4, 5, 6, you don't have to worry about the rotational directions. That's not true, because rotational constraints don't work if the elements connected to that node doesn't have stiffness in that direction. For instance, if you constrain solid nodes in 4, 5, 6 and think that's going to protect you from excessive pivot ratios, that won't work because the solid nodes don't have stiffness in those rotational directions anyway. So if you have a model where you suspect you have bad constraints, the solution is to basically constrain the model. Sometimes, this is like in this particular case, I would make the argument, good Lord, this guy's being slow. There we go. I would make the argument in this case that for this model, my model is actually load balanced. You know, I've got 100 psi here, I've got 100 psi here. So basically, I don't think this model really needs to run with constraints. If you have a model that basically the loads are already balanced, or maybe the model is actually flying through space, a second solution is to use something called inertia relief. If I get a chance, I might actually run a couple of these test models with inertia relief turned on just so you can see what it looks like. I really hope that maybe in one of my future Sim Academy presentations, I can actually cover inertia relief with you guys. And again, you know, if you've got a model with bad constraints, I recommend you add extra constraints. Or if you make the argument that this model should be free, you might be able to use inertia relief to get it to work. Let's go ahead and take a look at this model's results. If I scroll on down, I find our favorite fatal error message, 9050, and right above it, it basically says, one of my nodes is missing a constraint in T3. Well, in this particular problem, that doesn't mean you should find node 1198 and constrain T3. What you should do is take a look at this model and figure out, you know, maybe you're missing a constraint in T3 somewhere. Some of you guys might be wondering, you know, for those of you who use Patran, how would you find node 1198 really quickly in this model? I have two ways to do that. I usually go to Utilities, Display, and there's a tool here, Fem Label Tool Plus. And if you want to find node 1198, I just basically type in here for select, I'll basically tell it to label what I want. The object is going to be a node. But I can tell it to label elements or MPCs or element nodes or MPC nodes. So what I'll do is I'm going to label nodes, and I'm going to type in n space 1198. And if I click apply, here's node 1198. Something I mentioned earlier is that, you know, you don't look specifically at this node, you look at the area around this node. Nastran's basically saying a whole bunch of nodes aren't constrained in the TZ direction. Again, I can tell because you notice this sign is negative. So generally a negative sign means you should probably look at constraints. You know, the other thing is it's basically saying this whole model is not constrained in TZ, but the first one it found with that problem is this guy. this model, being a flat two-dimensional model, there's no load in TZ, so really I can get away with constraining anything in TZ and this model will run. However, when you guys get to your models and you find an error message like this guy, again, maybe if you see a negative sign, it means you should look at the constraints and then look at the area around this problem node, and then this guy gives you a hint as to what direction has the problem. So if I go ahead and modify, create a new constraint, constraint in Z to keep Nastran happy, and I go ahead and add a constraint in Z. For the application region, I can I'll just go ahead and constrain everything in Z. Again, the reason I can get away with that in this case is because I don't have any loads in Z anyway. My loads were purely in X, Y. Oh, it doesn't like the name. My name's too long. There we go. So now if I run this guy, job finishes, and now if I run this guy, the job runs successfully. And I can look at the results. So again, I just reran the job, I added that Z constraint. Here's something that we're going to look at towards the end of the presentation, this value called epsilon. So just kind of take a look at this guy. You might want to take a look at him after this presentation as well. But let me read in the results. And let's see, I want to plot my stresses. I want to make a deformation plot based on my constraints. And there we go. Let's take a look at the other most common cause for excessive pivot ratios, bad connections. So sometimes you might have elements that are not connected to each other. The first thing you should do, if you suspect this might be a problem, again, let's just suppose you run a model, you get excessive pivot ratios, and you get another one of these ones where the matrix to factor diagonal is negative, so you suspect it's probably bad constraints, or possibly elements that are not connected. How do you know if elements are connected together? We use what's called a free edge plot. So here you go, a free edge plot. What's a free edge plot? It's basically a plot of the free edges in your model. That's not a very useful explanation, so what's a free edge? A free edge is an edge that is not shared by multiple elements. It's an edge that only belongs to one element. So usually a free edge inside your model can indicate cracks or areas where things are not connected. When you're looking at a free edge plot, you're looking for two things. You should only see free edges on the corners of a solid mesh or the outline of a 2D mesh. Don't bother using a free edge plot if you've got a 1D mesh, because it wasn't meant for 1D elements. If you've got a 1D mesh, you want to know if things are connected, turn on the element labels or node labels and see if you have any nodes that are overlapping each other, or just do an equivalence command. There's a brute force approach that we're going to look at very soon. One question that comes up when customers do free edge plots is if they have a solid TET mesh, they actually find the free edges show up as dashed or broken lines. Holy moly, it's already 8:23. Where'd the time go? Basically, if you've got a TET mesh, a lot of times what will happen is that it can fill a corner with one or two or multiple tetrahedral elements. There's no reason why one's better than the other, and it's actually completely random. So if you have an automatic TET mesh, you have an automatic mesh in the solid, and the mesher just decided to fill the corner with one element, you're going to get a free edge on that corner. On the other hand, if a corner is filled with multiple tetrahedral elements, and again, this is completely random, you won't get a free edge plot there. So oftentimes when you have a solid TET mesh, corners will show up as dashed or broken lines, and that's actually very normal. when you're looking at a free edge plot, there's one other important thing to consider, and that's after you've used free edge plots for a while, you kind of expect certain free edges to be there. If you ever find there are missing free edges, so for instance, you've got a 2D mesh and you don't see the outline as free edges, or maybe there's a corner that isn't drawn at all, you might have duplicate or extra elements. Sometimes surfaces get meshed twice. Maybe a copy command was done wrong, but you might have duplicate elements, and that's what's causing these free edges to be missing. Let me go ahead and bring up a model with some free edges. We'll take a quick look at it. Good Lord, this machine wasn't this slow during yesterday's dry run. Let's see. We'll go to number 3. Bear with me, I need to get back to that directory. Actually, this one's going to be better. So here, I've got a model, and if I go to the elements, in Patron, if you want to bring up a free edge plot, you go to the elements menu, and then do an action verify object elements test boundaries. And this is an example of a model with potentially problems. So, for instance, the free edges should only show up on the corners of a solid mesh. You'll notice here I've got free edges on the inside. So basically this free edge plot is telling me that this mesh and this mesh back here are completely separated from each other. Also, if this was connected properly, you'd actually see, like for instance here I've got a shell mesh sticking out of the solid. This is going to cause problems later, and we're going to discuss that. But basically, if this edge was actually merged in with the solids, you shouldn't see a free edge here either. But I do. So basically, this is telling me that for this particular model, this shell mesh, and this solid, and the other solid behind it are not connected together at all. If you have this problem, there are 2 ways to fix it. So meshes that are not connected can be fixed simply by using the equivalence command in Patran, or in other packages it's called merging coincident nodes. That only works if the meshes match up to each other. So for instance here, I am lucky that all these meshes, they do match up to each other. So if I wanted to connect them, I could just use the equivalence command. Or you may have to delete the mesh, break up the underlying geometry to get things to match up, and then remesh, and then re-equivalence. We've had something in Nastran for a while, and starting probably early next year, or possibly even late this year, we're actually going to be releasing it to all customers. So starting pretty soon, all customers will be able to use full 3D contact using Nastran. Well, when I say all customers, you've got to be using the newest version of Nastran or a recent version of Nastran. But if you have access to one of the newer versions of Nastran using Sol 101, you could actually use what's called glued contact. So when you use glued contact, like if you look at this model, in this particular model, I purposely left it disconnected, and then what you can actually do is define a contact body. So here I've defined this entire back solid as one contact body. Let me go ahead and do a plot contours, plot the contact bodies for you guys. So this guy in green is one contact body. This guy in yellow is another contact body. And this guy in blue is a third contact body. And then what I can do is, when I run the analysis, I define a contact table. So if I look at this contact table, you'll notice that, for instance, the back solid is glued back solid is this guy in green is glued to the yellow guy over here. So that's what this table is telling me. And then the appendage, this surface mesh up here, is glued to the solid at the end, and that's what this is telling me. If you want to brute force it, you could actually turn on all the entries in this table, but here I want to try to keep this running as quickly as possible, so I actually went ahead and only highlighted the entries that I need. G means that it's glued. In this particular case, to get things to work properly, I actually had to turn off, basically if I go to the options, I have to basically tell it to ignore thickness. And then I also need to tell it, in order to get this to work, I also have to tell this glued connection to transfer over moments, specifically because this is a 2D element. It has stiffness and rotational directions. This guy is a solid element, has stiffness only in the translations. These rotations, these moments need to be transferred over, so I've got to toggle on this retain moment. Let's see, this machine's running really slow, so let's take a look at, and I'm getting close to my 45 minutes, and I've got quite a bit more to cover, so if we take a look at these results, let's see, here we go. If we take a look at the results, let's see, we do see this entire guide deforming as one block. This gives me a chance to cover something that's not related to this presentation, but is a question that comes up quite often. Whenever you've got multiple types of elements, sometimes customers want to be able to do a fringe plot on, for instance, in this case, a customer might want to do a fringe plot on the solid and the shells at the same time. Customers ask me, how would you do this? I would actually go to Create Fringe, and let's see, let's go ahead and make a fringe plot on my stress tensor. And the reason why it looks black like this is because I'm looking at stresses only on, in this case, the solids. Z1 and Z2 means I'm looking at stresses on the shells. If you want to be able to look at stresses on the solids and the shells at the same time, you can go ahead and highlight all three. Now, the problem that's going to come up is, what do I do about the shared boundary here? I'm going to see multiple stress values here. How do I pick one to make my stress plot? I'm going to tell it to just show the maximum. I can do that because I'm actually looking at the von Mises stress. So let's go here. I'm looking at the von Mises stress, which is always positive. If you're looking at a directional stress like X normal, Y normal, I recommend you do this plot twice. Once with maximum, once with minimum. But again, if you're looking at something that's always positive like von Mises, you can get away with just showing the maximum. If I click apply, I can see the stress in both at the same time. Here is a very important point. If you do this, I really recommend that you go to the plot options and set the averaging domain to properties. Why? Because what happens is that at the area where the shell touches the solid, you get very different stresses. You don't want to average the shell stress to the solid stress with each other. You're going to average out the highest stresses in your model. So basically, if you do this trick, I really recommend you go to plot options and change the averaging domain to property. This basically tells Patran shells get averaged together, solids get averaged together. Do not average the shells to the solids. Let's see, what else can I tell you about this? This particular setting for the plot option, the average domain, is only available under Create Fringe. So if you ever try to make a color plot for bars and solids or bars and plates or shells and solids, don't use Create Quick Plot. Go to Create Fringe. That way, not only do you have this layer control where you can highlight all of them at the same time, but you also have the plot options where you can set the averaging domain. So hopefully this is a useful tip for you guys. The other possible cause for excessive pivot ratios, when I say bad connections, is you're mixing element types together. So for instance, in this model, I'll get excessive pivot ratios, and I'll show that to you guys in a moment. But the reason is because I'm mixing solids. So let's take another look at this. I'm mixing solids with shells. And one possible pitfall you'll notice is that solids only have stiffness in the translational direction. Solid nodes can only take forces. Shells, on the other hand, have 5 stiffnesses to work with. They have Tx, Ty, Tz, Rx, and Ry, no Rz. Unless you're using Nastran 2005 or later. I'm going to have to double check this date for you guys, or this version number. But basically, customers said, this causes a lot of problems not having the RZ stiffness. So starting in 2005, we've been trying to find ways of adding this RZ stiffness into the shell. So if you look up a shell element in a classical mechanics of materials book, you'll find that the actual 2D formulation only has stiffness in 5 directions. If you're using 2005 or later, we actually are developing new formulations that include all 6. Either way, what's going to happen is that these shells have stiffness in rotational directions. The solids do not. So, in essence, the problem is I have a hinge here. And if you don't fix this hinge somehow, you're going to get excessive pivot ratios. So let me bring up this other model. Sorry for the delay, guys. Apparently there's a lag between what I click and what actually happens due to the fact that I'm sharing my screen through WebEx. So here's a model that I've made. This is that same model as before. I'm going to show basically how would you solve this without using glued contact. The problem is that if I look at the free edge plot, it actually looks good. So this model's free edge plot is exactly what I would expect. I only see free edges in the corners of my model. All the corners have free edges, so there's no duplicate element problem, at least that I can see from here. Notice that I'm missing a free edge from here to here. That's basically telling me that this shell mesh is glued to the solid mesh. If I go ahead and run this guy, so let's go ahead and bring up the FO6 really quick. This PDF is going to be called Shell to Solid. And if I scroll down, let's see. One other thing that a lot of times you might find is this grid point singularity table. This does not necessarily indicate a problem. This is basically telling me that for some reason, some of my nodes don't have stiffness in 4, 5, and 6, the rotational directions. Their stiffness is actually 0, and that Nastran has decided to constrain this. This is a report from a setting called AutoSPC, the Automatic Constraint Systems in Nastran. It's telling me that basically my nodes don't have stiffness in the rotational direction. I don't consider that a problem because I'm using solid elements. Solid elements don't have stiffness in rotations. So this is basically telling me that the rotational directions have been constrained out. And it's listing it for every solid node in this model. If you guys want, give me a call to tech support, drop me an email. I can cover AutoSPC in more detail with you guys. There are ways to suppress this report. If you ask me the quick 5-second explanation for what this is, Nastran has found stuff that doesn't have stiffness. AutoSPC constrains that out. What do you need to be careful about? Well, this is basically telling you that if you have any loads in 4, 5, or 6 on these nodes, that load will go nowhere. So if you ever see this grid point singularity table, this is basically telling you don't have any loads in these directions in this model. It won't, the load will be ignored. In this presentation, I care about the excessive pivot ratio error. Notice that it's telling me that I have a problem with node 11077, and it has a problem with the R2 direction. If I actually find this node, dear Santa, please get me a faster computer. What was the node number again? It was 11077. So I want to find node 11077. And basically, it's kind of faint, but there's a red dot that's just shown up right here. So that's basically my problem node. It's saying that something's wrong around this node. And specifically, the problem is that you don't have a constraint, or you don't have a connection in the rotational direction here. So long story short, these solid elements don't have rotational stiffness. These shell elements do. I have to find some way of connecting the rotational directions. Let's see. There are a couple of ways of doing this. Either A, find a way to turn off the rotational stiffness. Not possible with these. Shell elements, in this case, I have a shell element that I'm putting specifically in bending, so turning off the rotational stiffness means, or constraining it, means that I'm going to have bad answers. A second possibility is you can use rigid elements to couple out the rotations. That's what I'm actually going to do very shortly. Or newer versions of Nastran, and I'm actually very excited about this, you can actually use glued contact. Glued contact is basically what most of our development effort is going to right now. Glued contact would allow you to basically connect this shell to this solid. The meshes can be completely different. This could be a quad, this could be a tet, this could be a quad 4, this could be a tet 10. That's a very common situation, and the glued contact would basically take care of that, and you wouldn't have to make sure that the meshes line up. The RVE solution that I'm about to do requires that you basically have two lines of nodes for everything to match up. Another question that comes up is that, here I am. I've used Nastran for a long time, so I spot these problems pretty quickly. Another thing is that I don't actually work for a living, so all my models are simple blocks or plates by themselves. If you have an industrial-sized model, finding bad constraint or bad connection problems like this is literally like finding a needle in a haystack. So if you have a larger model and the bad constraints or bad element connections just aren't popping out at you, you just can't see it, another possibility is to run a normal modes analysis. A lot of times, a model that fails due to excessive pivot ratios will actually run in normal modes. That's what I'm trying to say right here. Basically, in linear statics, Nastran blows up when the stiffness matrix goes to 0. But in normal mode, Nastran's trying to find specific situations where the stiffness matrix goes to 0. So when you run normal modes in a model with excessive pivot ratios, what are you looking for? You're looking for eigenvalues or natural frequencies that are close to 0. And when I say close to 0, it won't be exactly 0 due to round-off error. So, for instance, I'll be looking for something around 1e to the minus 6 or smaller. Let me go ahead and run this guy while I'm lecturing you guys on this. Solution type, normal modes, okay, and that should be good to go. So job's running right now, and again, since this model is a model with excessive pivot ratio problems, I'm looking for eigenvalues or natural frequencies close to 0. When you do, plot these mode shapes. That will tell you what direction needs to be constrained. It will tell you where the mechanism is. When you have a rigid body, if you run a model with no constraints at all, so you run a model free, there should be 6 rigid body modes. 3 rigid body modes for the translations, 3 for the rotations. One important thing is that if you ever run a model free in normal modes, and look at these 0 Hertz modes, you're going to expect 6 in that case because the model's not constrained. And basically, if you plot those mode shapes, they will not necessarily line up with any particular coordinate system. So if you ever run a model free in normal modes, don't expect the first mode to be a rigid body mode in X, Y, or Z. It might run off in some seemingly random direction. But your first and rigid body modes will be 3 translational rigid body modes. They will be perpendicular to each other. They just won't line up with any particular coordinate system. Very important thing. If you ever run a model and you get more than 6 rigid body modes, like you run it free, you get more than 6, that means there are multiple connection problems in the model. One other thing is that if you run a model that fails with excessive pivot ratios, don't expect it to always run in normal modes. I find about 90% of the time it does, but sometimes it won't run because either the pivot ratios are too high or there are just too many rigid body modes for Nastran to sort through. In this case, even a normal modes analysis won't run. But hopefully, if the model's that bad, you'll be able to spot the problem anyway. Here, let's see. Search, find. I am almost out of time, so I've got to wrap this guy up. Eigenvalues. Here's my eigenvalue analysis summary. Notice I've got at least one eigenvalue, natural frequency, that's very close to 0. 3e to the minus 4 might as well be 0. Its generalized stiffness is negative. That also indicates it's a rigid body mode. If I go ahead and read in the results, you'll notice the first mode is very close to 0, and if I go ahead and plot this deformation, this is basically telling me that my mechanism is here. Basically from here, your solutions are to either, and basically it says here, I need to find some way of constraining this out somehow. My recommendation is, in this case, is to use glued contact or to use what's called a RBE2 or RSS-con. Let's see. Another possible reason could be because something has very high stiffness or something is very low stiffness. And when I was reading this last night, I realized this is a very vague statement. Basically, what I'm trying to say is that Nastran is okay if your stiffness is infinite. In that case, you use an RBE2. Nastran is okay if your stiffness is 0, because if your stiffness is 0, that auto-SPC, the automatic constraint system I talked about, will take care of that. However, if your stiffness is very close to infinite or very close to 0, that can cause excessive pivot ratios. That's what we're going to see in the following model. Assuming my computer lets me. Oh. I suppose I should be more patient. Okay, so in this particular model, seems like a simple enough model. What I've got here is 2 cylindrical shells. There is an RBE here, just so I can do a constraint. There's an RBE here, so I can do a load. And something is in between here. It could be a bushing. It could be a component box. It could be a fastener, but something is in between here, and so I've approximated this with a C-bush. Show element attributes. So I approximate this guy with a C-bush. And this C-bush again, I should be, oh, there we go. This C-bush, say it's some kind of a soft rubber bushing that I've decided to put in here, has a stiffness constant of basically 1. If I run this, I'm actually going to get excessive pivot ratios again. not that one. Here we go, this guy. So I get excessive pivot ratios again. In this particular case, it's not a problem with connectivity. It's not a problem with constraints. The constraints are actually good. The problem is actually from the fact that these stiffnesses are so darn low. Oftentimes this issue comes up. Sometimes customers, when they're using a C-bush element, will just end up defining arbitrary stiffnesses. For instance, if there's a bushing right here, you might only want to make a C-bush only in the axial direction. Well, if it's only in the axial direction, what do I do about the other stiffnesses? A lot of times customers will do a very valid thing. They'll just go ahead and make up extra stiffnesses just to keep Nastran happy. So for instance here, I only really need a stiffness constant in the one direction. I go ahead and fill in stiffness constants for the other direction. But the question that comes up is what stiffness constants should I put in here? Usually, if you want to model something that is very stiff, you'll want to make it 1,000 times stiffer than the area around here. If you want to make something very flexible, you'll want to make something 1,000 times more flexible than the area around here. The question that comes up is, how do I calculate the stiffness around this area? The most common pitfall customers do is they look at the material, and then from the material, they basically say, oh, my elastic modulus is 30 e to the 6. Well, that means the stiffness here is 30 e to the 6, right? Not true. Stiffness is related to the elastic modulus. E indicates stiffness, but it's only proportional to the stiffness. So whenever you guys are making spring elements and you're just making up a couple values to basically keep the solver happy, you got to try to get it somewhere in the ballpark of the stiffness of the area around it. Again, if you want it more stiff than the rest of the structure, make it 1,000 times stiffer. Want to make it more flexible, make it 1,000 times less than that. If you ever want to find the stiffness, just a quick calculation for the stiffness around something, well, then in that case, what I actually did is I basically looked at one of the cylinders, and then I went ahead and put an enforced displacement. I basically put a load on here. In this case, the load I chose to do was I basically constrained one end, and I put an enforced displacement here, and the enforced displacement is a value of 1.0. If I zoom in, you should be able to see it a little easier. So you'll notice here, I've got an arrow here showing 1.0 and a constraint of 2, 3, 4, 5, 6. So, long story short, if you want to see what the stiffness of your model is, put a load on it. You put a load on it, and then you look at the displacements. And F equals Kx, so the stiffness is going to be the force you applied divided by the displacement that you get. And that gives you a rough ballpark for the stiffness of this area. In my case, I try to be a little clever about it. I apply a unit displacement because, again, F equals Kx. So if x is 1.0, then basically the constraint force of this applied displacement is going to be the stiffness of this area. Let's see. If you want to look at this stiffness, it turns out the stiffness of this cylinder is going to be 2.25 e to the 6. So if you're making a push in this area for the y and the z, the rx, ry, rz, if you want to make those stiffnesses larger than the rest of the area, then you want to make it 2.25 e to the 9. If you want to make it softer than the rest of the area, you'll want to make it 2.25 e to the 3. That way, you get the flexibility you want, or the stiffness you want, and you won't get excessive pivot ratios. Sometimes, like if in the axial direction, for instance, what if the stiffness actually is 1.0? What if that's the stiffness you actually want? Like in this case, I'm trying to tell you guys some guidelines for fictitious stiffnesses just to keep the solver happy. But what if it's an actual structural stiffness that you care about? So, like in this case, I've got stiffness values of 1.0, and that's basically a value I got out of a table based on properties of a bushing. If you have to use that stiffness value, then in that case, you'll want to probably go ahead and adjust the tolerance of max ratio or use param bailout. Param bailout's purpose in life is to basically tell Nastran to basically run, and if you find a matrix conditioning problem, let it roll and give you answers anyway. Max ratio is similar to that. Max ratio is more controlled. Max ratio says how big a stiffness issue problem do you allow and still give results. So basically, if you took max ratio and made it infinite, you'd get bailout. If you decide to use these two parameters, you will get results. However, I really recommend that if you use these two parameters, look up a parameter called epsilon. So, for instance, here, this model fails with stiffness ratios around e to the 7. So I can actually tell Nastran to accept a stiffness ratio this large. So, for instance, I can go here. I'll actually use the direct text input because Patron doesn't have an interface to use the max ratio parameter. So, under the bulk data section, I can either do param, bailout, -1. I can't stress to you guys enough how dangerous this setting is. This setting can basically mask problems that you might be having in the model. Or I can use param max ratio. Let's just use 1E8. So basically, it's going to tell Nastran that if you find a stiffness ratio this big, let it roll. So now the model runs. Now that I've used this max ratio setting, I'm going to get results that I can look at. But really, remember that Nastran had that warning in there for a very good reason. So when you're doing this, you really ought to look up the error parameter epsilon. Epsilon is a measure of the round-off error in a model. So if you ever use max ratio or bailout, our warning is that it may give you bad results. How do you know if you've safely used max ratio or bailout? Because I've found that many very good, very smart engineering groups do use max ratio and bailout successfully. How do you know you're one of those people? Look up epsilon. Epsilon is a measure of the round-off error in a model. It's calculated by doing f minus kx. You know that f equals kx, so if you do f minus kx, it should be 0. It's not going to be due to round-off error. F minus kx is basically has a units of load. It's going to be a long list of numbers. So what we do is we multiply it by the displacements to get a work number. Work is always positive, and it's one number for the whole model. The only problem is that we want to know if it's a big or small value, so we normalize it by a known value. We normalize this by the strain energy in the model. So once you do this, you get a normalized single number that gives you a feeling for the error in the model, and that's going to be epsilon. Epsilon indicates how many decimal places your displacements are good for. So, for instance, an epsilon of 1e to the minus 16 means that you have displacements that are good to 16 decimal places. If you get an epsilon of 1.0, it means you have displacements that are good to no decimal places. Don't use that model. Personally, for me, if I ever see an epsilon that is 0.001 times my max displacement, then basically epsilon is too high. I would have serious doubts about that model. In this particular case, I have an epsilon of 0e to the 0. Let's see. In this particular case, that's not actually a problem. It's actually user error. To have an epsilon that small, it basically means I've accidentally run the model with no loads. Let's see. If I have time after question and answers, I can go ahead and rerun this model and demonstrate to you guys, what an epsilon should look like. But when you guys get a chance to go back to your desks and work with Nastran, I recommend you do that as well. One last thing, just so I can wrap up. When you get to pivot ratios, sometimes it can happen because a customer switches Poisson's ratio with new with G. So, for instance, if you ever have a model, you basically, no matter what you do, you can't find the excessive pivot ratio problem, look at your materials. Make sure your thickness, make sure your moments of inertia are good, and then look up Poisson's ratio and G. Make sure you didn't actually switch those two values. Another possibility is if you're using springs or rigid elements. Sometimes the customer will accidentally cross their wires. In other words, they'll accidentally connect X to Y or Y to Z. Stiffness for a spring, rigid element, or bush should always connect X to X or Y to Y unless you really know what you're doing. Generally, this will happen because the nodes have different output coordinate systems. So, long story short, if you suspect your RBEs, springs, or MPCs or bushes are the problem for excessive pivot ratios, look at the output coordinate system of the nodes. Make sure they're the same for the entire element. Let's see. I am out of time, but again, for this particular topic, it's a simple topic, but it's really surprising how long we can talk about this to find the possible problems. Are there any questions?
Yeah, folks, thanks, Lee, for a great presentation. Go ahead and type your question into the Q&A panel, and we'll read out loud, and we can answer them if you have any questions right now. And again, I've got a couple of people that are asking how they can get this cheat sheet that we had kindly created for us. I've put a link on the chat panel with to the placeholder page on our Sim Companion site that will have Lee's cheat sheet as well as an archive of this video. So check, tomorrow or in a couple of days, it'll be there.
Might even be up before the end of today, maybe even a couple hours.
Perhaps, but definitely tomorrow or the next couple of days.
Also, this cheat sheet is something I've spent the last week or so writing. It's, nowhere near done. Personally, for me, my goal is to keep this thing less than 5 pages, because if it's longer than 5, I don't think it's very useful. But, when you guys get a chance to download it, or if for some reason you can't find it, send me an email. I'd be happy to email this to you guys as well. Or go to the Sim Companion page. You can download it yourself. And I'd love feedback you guys have on extra topics, or maybe you guys have some edits, or maybe you found a mistake in there. We've got a couple questions. I'm going to try to cover them as best I can. Adrian Niegu, he's got a question. What if you select none instead of property or averaging? Adrian, that is an excellent point. If you select none, you won't average anything with anything. I think that actually gives you the best answer, because when you average, you take the highest stress and average it with something else, which means you get lower stresses. The problem is that managers like smooth color plots. Some managers think if your stress plot doesn't look smooth, it isn't very good. So I actually do a little bit of averaging just to keep everybody happy. If I had a choice, I would actually set the averaging to none. Adrian's got a second question that basically said, early MSC documents recommended transferring moments from shell to solids by coating the neighboring solid with a thin layer of solids. Is this still acceptable? Adrian, I think the argument that you're making is very interesting. In some cases, I would say yes, that's acceptable. In other ways, I'd say no. Let me explain. Let me open up that model that has the shell to solid and try to explain what I'm trying to say. Here we go. Adrian's basically saying that this particular excessive pivot ratio problem where the shell connects to the solid could be solved by coating it with a thin layer of shells up here and underneath the shell as well. I think that's actually not too bad a way to go, and the argument I would make is this. In the finite element world, this has no thickness. But in real life, this shell does have thickness. So basically, what I'm saying is that in real life, this thing wouldn't connect to a line of contact. It would actually have a full surface of contact. So if you, for instance, refined the mesh to make this around this joint, and then put a skin of surface elements just along here and here, you might actually get a good answer. Where I disagree, where I think it might be a bad idea, is some customers will basically put the shell elements inside the solid here. That will also get the model to run. However, the problem is that if you do a shear and bending diagram, what happens is that a bending diagram should show zero bending moment here and then show maximum bending moment here. And this is where you should get the highest stresses. However, if you put a shell element inside here, the problem is that your bending moment will actually go down and then somehow magically increase inside the solid. Some people argue that is what happens in real life, but for me, I prefer a conservative model. So, I don't like putting shells inside the solid. Plus, you have to imagine, what would that represent in real life? That would represent in real life that somehow you gouged material out and shoved the plate inside and then welded it in. Maybe that is what happens in real life, but that isn't a common manufacturing thing. So I think in real life the weld would actually be up along here and down here. So in that case, putting a thin layer of surface elements up here and down here isn't a bad way to go. If you want, the problem is that if you make those extra skins too stiff, you might introduce new excessive pivot ratios. And again, if you make it too soft, you might introduce new excessive pivot ratios as well. And that's why a lot of our developers are working on glued contact or ways of connecting dissimilar meshes together. Hopefully that answers your question, Adrian. Jason's asking, will you email us your cheat sheet? Jason, most definitely. Jason, do me a favor. Here's my email address. Drop me an email. I'll be happy to email it out to you. Let's see. What was the utility I used to highlight a desired node? Or, Edwin's got his eyebrows raised over here. I will upload this cheat sheet to our Sim Academy page as well. So, you guys don't have to email me directly. Just go to the Sim Academy link that we'll have, and you'll be able to download the Word document. Let's see. Jason's asking, what's the utility I used to highlight the desired node? Jason, that utility was Utilities, Display. I'm sorry, my Patron's being a bit slow. Utilities, Display, Fem Label Tool Plus. One other tool I find very useful, let's suppose that I've got a problem with node 1198. I can go ahead and make a node with just node 1998. So, bad node. So, N1198. So I make a group with just that bad node in it. If I post that node, it's not very useful because now all I have is one node. There's actually a utility to expand the group out. If you look under Utilities, Group, Group Extend plus MPC, this will actually, let's see, let's just go to Posted. This will actually expand that one node I've selected to the elements around that node. And I can actually run this multiple times to expand this out. So if you get excessive pivot ratios and it says you've got a problem area, you want to look at the area around it, I recommend two tools. Utilities, Display, Fem Label Tool Plus, and also you can put that bad node or element inside its own group and then use this group Extend plus MPCs. Any other questions? Again, I'm sorry for going through this so quick, and we only had 45 minutes. Feel free to call us up on tech support. If I'm lucky enough to teach a class with you guys, feel free to we can talk this over a lot longer. And thanks for your time.